Okay.
It was in lecture 11. I know the example that you used was from the book about a cooling off.
Yeah.
And so that problem was in the book on, it was an example in the book on page, let's
Yeah.
see,
I
it was
changed
on
it up a
page
little bit.
88.
Yeah,
Yeah,
I
so
changed it from the example just slightly.
I'm just trying to understand in that example, how do they come up in the book, how they came up with the time in minutes based on the temperature? Because that problem really doesn't, when you went over it, you just kind of just came up with a formula and said, this is T and this is K and but how do they come up with those times in minutes?
Oh, okay, so it all depends on so you have some differential equation, right? You have some differential equation, and remember how you always have like it's like a sample data point, right? Okay, so you take the pie out of the oven, right? But you're sampling it after after a certain point in time, right? So after 1 hour you sample it, or after 5 minutes you sample it, or whatever. But whatever units of time that you have when you're sampling this, that kind of configures up the problem so that if you
So
measured what the
basically,
if you
so,
measured
so
what the
basically,
temperature is after 4 minutes, then it's all in minutes. And if you wanted to do hours, you'd have to convert it.
well, okay, so in that example in the book, it had figure 3.1.5 on page 88. It had temperature 75 degrees and the time in minutes was 20.1. So basically, what we could do is just put in whatever temperature we want, and then we can come up with the time.
What is that? Okay, so let me try to just make it very clear. Okay, I'll try. So the pie comes out of the oven, right? In order to solve for that constant, right, the K, right? By the way, there's several different constants, as you know. But in order to solve for that K, which is like in the population constant, it's the growth or decay constant. Anyway, it's a little bit different in the temperature one, but same idea. The whole thing is you have to take a sample data point of that of that situation to plug it into the differential equation to get your K. Okay. So the whole thing
Okay,
is
so
that
basically, yeah, so they were just taking in that example, they were just taking they put 70 in there because 70 was the K, which is the constant, but in that figure 3.1.5, they were just using 75, 74, 73, 72, 71, and 70.5. They were using that as the constant to figure out what the time was.
yeah, and again, you can always convert time into whatever you want, but usually the way it is that if you do the experiment and then you do a data point after 30 minutes, then the problem is set up for it to work in minutes. Okay, so if you had said, oh, after 1 hour, then we have a certain temperature, then it would be set up for hours. Okay, so another thing is that it was kind of confusing what they did in the book, and that's kind of why I changed it. And I just said, hey, just find a function in general with respect to time, because they kind of did some weird, complicated things. So if it confused you, don't worry about it, because they worded it kind of weird. But the whole thing is time can always be converted from minutes or seconds, but usually if you take a sample data point and you take it after 30 minutes, then time is in minutes. That's what it
Yeah,
is.
well, I'm really curious about that because I used to run into stuff like that at my old job, and so that's why kind of I wanted to nail this stuff down. So
Yeah. So that's the whole cool thing about this whole subject, that there's a lot of people that say, when are we going to use this? When am I going to use all this math stuff? Hey, anytime something heats up and then you whatchamacallit, you cool it down, you could literally model stuff using this equation, and this is valid. So yeah, so and it's fun to do. So you could always do your own experiments, and try. You just need like a thermometer or something, and so you can cook a turkey, get a thermometer, and take it out, and after 5 minutes, measure the temperature, plug it in sulfur K, and then try to see how long will it be until you don't want it's lukewarm and you don't want to eat it anymore. Okay. So I got all of the exams. Everybody turned in all of the exams. I still have one more to grade, and I'm going to be emailing these back to you. Okay. So I wrote like corrections on these. Okay. So I like graded it so you can see how you did or what you missed, and I wrote notes on this. So you'll probably get that sometime this week. You'll get the exams back. Everybody so far did pretty well. Okay. So I'm happy to see that. And yeah, and if you send me something and you didn't get like a response or whatever because I entered all the grades into Blackboard, um, whatchamacallit, because somebody, I think maybe one of the exams slipped into my spam folder, and I wasn't even thinking about that. So unless somebody, we figured it out. Okay. So anyway, so all is good. So yeah, so okay, so in this section, we're going to be doing section 4.1. This is just the name of the section. It's called preliminary theory. Okay. I'm trying to write really nice on here, but it comes out all sloppy. Just bear with me. Okay. So yeah. Okay, so you know how there was the IVP problems? Okay, we did that. They just give you like a point, or they give you a derivative in a point. Well, there's also something called BVP. Okay, so BVP is boundary. Okay, boundary value problems. Okay. And so basically, you're going to be given a bunch of points, right? You're going to be given, like, X, what is it? Something like this. You're going to be given some points, okay? And you basically plug them in to get C's. C's are constants, okay? So anyway, so we're going to do that in just a second, okay? So if you know how to do the IVP problems, this is basically the same thing, but it's important to know. So give me 1 second, because every time I do a session for this class, I have like a special folder, and I try to set up a special folder that has the notes for every day. So that takes me like a second to set up. Okay. All right, we're good here. Okay, I'm going to clear this. Okay, so what if I give you this, okay? Okay, what if I gave you this guy right here? And again, this could have been y, it could have been in terms of y, okay? It could have been y double prime plus 16y. In this case, it's just x, okay? But you could substitute, y's, x's, or whatever. It's in the same format, okay? So here's some differential equation. And the thing is that I don't think okay, this looks familiar, right? Doesn't this look familiar? In fact, I think this is, yeah, this is linear, right? This looks familiar. But the thing is that, here's my question. Have we, have, have we done, solved any DEs with a y double prime or x double prime? Have we done anything like that? Because I think this is called like second order, right? Yeah, I don't think so. So what's so interesting, okay, here's the interesting thing about all of these DEs, okay, the differential equations. We've solved all kinds of stuff so far, right? But then here's this new problem and we haven't solved it, and it looks very familiar. All it is it just has this one extra term here, you know, y double prime or x double prime. Looks really familiar. It looks familiar, like we've seen it before, but we've never done anything like this. So the things that just so many different types of DEs to solve. But anyway, we're not going to solve it right now, okay? What I'm going to do is I'm going to give you the solution, okay? So the solution is this, okay? It's C1 cosine, okay, plus C2, we have sine. Okay, great, so we have this, right? Okay, so you can always check to see if this is a solution, right? You could always, you know, to check to see if this is a solution, you can find x prime and then x double prime, right? And then plug them in, see if it's true. Anyway, also note this, okay? This is interesting. Remember, the cosine and sine functions, they flip-flop, right? Okay, cosine sine flip-flops. So if you really were just looking at this differential equation and trying to see how to make the left-hand side 0, you might be looking for, okay, think about it like this. This is really interesting, okay? You might be looking for some type of function, right? You're looking for some type of like f double prime that cancel out with the original function, right? And we know that the cosine and sine functions do that. Um, because, what is it? If y equals sine, right? Okay, y prime is cosine, but then y double prime is negative sine. So the thing is that even without knowing any techniques, right? Any techniques on how to solve this, right? We haven't learned any yet. Even without knowing any techniques, you can basically look at this from a theoretical perspective and say, oh, we have an f double prime that needs to cancel out with the original function. Oh, how do we do that? Look at this right here. Look at this right here. If we just had, y double prime, like plus y equals 0, then this would have been the solution, right? Because sine minus sine is 0. So anyway, so that's why this has the format. Of course, it's a little bit more complex, but you can look at these DEs and try to make sense out of them, even if you don't know how to solve them. That's pretty interesting. Okay, so let's look at this. Okay, so this right here, okay, this right here is a given solution. Okay. Okay, so with boundary values, usually what happens is you are given a DE, you try to solve it, and then they give you these points, okay? For example, I'm going to give these points right here. X 0 equals 0, and x pi over 2 equals 0, okay? So these are the, how do I say this? This is the boundary values, okay? Okay, now these are just points, right? Okay, they're just points. And remember, it's x of t because of how we're writing things, okay? T is the variable, okay? So anyway, so if basically, so to do these types of problems, if somebody gives you a DE and they give you a solution, or you find a solution and you have constants in there, if they give you these things called boundary values, all you do is you just plug in the boundary values to solve for the C values, okay? So here we go. Let's do it. Let's take the first point, okay? 0 equals C1 cosine 4t plus C2 sine 4t. And I'm taking t as 0, and x of t is 0. So I'm setting the whole thing equal to 0 because x of t is the left-hand side. Okay? All right, so let's see what we get here. Okay? We get C1 cosine of 0. Does everybody remember what cosine of 0 is? And if you have to draw one of these little charts, that's okay. Okay, so sometimes I draw this out. I draw a unit circle and I just list stuff. Okay, I list stuff like this. Okay, and by the way, the unit circle, if you want to remember the unit circle really easily, just think it's just a circle. It's just a circle. Radius equals 1 on XY plane. Okay, it's just a circle with radius 1 on the XY plane. Okay. So when you try to find cosine 0, you're looking at what? You're basically you're looking at 0 angle, right? Okay, so this turns into 1. Okay, and everybody knows that. Everybody's been saying that. Okay, sine 0. Okay, sine 0 is what? That's 0, right? Because remember, cosine is the x value, sine is the y value. So we're looking here at 0 angle and just pulling these x and y values. Okay, so what did we figure out from this? Well, we figured out that C1 equals 0. Okay, great. All right, I wonder if I can squeeze the rest of this in here. Yeah. Okay, so what about the other boundary value point? Okay, we have x of pi over 2 equals 0. Okay, so let's plug that in. So I'm going to say 0 equals, I'm just using this equation right here with C1 and C2 in it. So 0 equals C1 cosine. I'm going to plug in pi over 2 into here, okay? And that reduces to 2 pi, okay? Then I have C2, and I'm going to plug in pi over 2 into here, and I think that also reduces to 2 pi. Okay, so how do we do this one? Cosine 2 pi is now 1, but sine of 2 pi is now, oh wait, hang on. No, I messed up someplace.
Yeah, I was wondering where you got C1 is equal to 0.
Okay, hang on. Well, I think C1 equals to 0 is correct. Um, um, but hey, I think I accidentally did something. So give me just a second here. Okay, okay. Here's the thing. Okay, I wrote up my notes for doing this. Yeah, yeah, exactly. Okay, yeah. Thought I was following them right, but apparently I made some tiny mistake in here or something. I think this one is correct, the C1. I know this is correct. Let me check again with, see, I tried to skip steps. Okay. You're plugging in pi over 2 into t, and you have a 4 in front of it, okay? Okay, but that just makes 2 pi, right? Anyway, okay, so, okay, here's the deal, okay? I'm going to give you guys this. This is my challenge to you. You're supposed to, okay, but you get the concept, okay? You're trying to solve for C1 and C2 using these 2 points, okay? Plug them in, see what you get. You should get something for C1, C2, and that's the whole idea of that, okay? So apparently I messed up somehow, but as an exercise, go home, look at this, plug these in, see if you can solve for C1, C2, because that's what you're trying to do. Once you get C1, C2, then you basically plug them back into here, okay? And so basically what's happening is, if you pick these boundary conditions, you get a certain type of solution that satisfies the boundary conditions, okay? So that's the whole deal there, okay? That's the main concept, okay. Okay, so more concepts, okay? We're going to clear this, and we're going to talk about more concepts. Okay, so remember how I was talking about how the derivative, it's is like an operator, okay? And I shouldn't even say is like, it is, okay? Derivative as operator, okay? So here's the thing. So what does the derivative do? It operates on something, right? So there's all these different types of notations that you can use for this. So for example, this is the notation we're all familiar with, right? We're all familiar with this, right? Take a derivative of some function with respect to some variable, okay? There's also another notation that they use in the book, okay? They use this in the book a lot, where they just put a capital D, okay? They put a capital D in front of a function in parentheses. And basically what that means is we are operating with derivative operator on this inner function right here. Of course, with this notation, sometimes it's easy, it's very readable, okay? But it's hard to know what variable you're taking a derivative of. Usually you'll know by context clues. I like to sometimes write a derivative like this, where you basically have open brackets, okay? But there are some mathematicians, literally, that will even write it like this, without even a bracket. So someone will just write d with nothing here, divided by dx, and that implies a derivative operator. And also, keep in mind that you can have multiplication operators. So, for example, if you see something like this, okay, I think sometimes you might see it with hat on it. Basically, if you insert a function into here, it'll operate on here by multiplying it by x, okay? For example, okay, if I have this, it seems, let me come up with something like this. If I have something like this, okay, I could have, you know, x cubed plus y, okay? But if this is a multiplication operator, okay, this is going to be this, okay? Very interesting how this works, okay? So anyway, let me print screen this and we will keep on talking. Okay, so the book talks about this concept called a polynomial operator, and we're actually familiar with this, okay? Okay, so remember how we talked about the definition of linear differential equation, right? It's something like this, right? Some type of coefficient we have, and then we have some type of primes, and basically this just goes in descending order all the way down until we basically end the polynomial, okay? So, and we all have decided that we're gonna consider this linear, right? Okay. So you can write this, okay, in another way, okay? And this is called a polynomial operator, and they call it L, okay? And basically, it's the same thing that we have done here, but they're going to use that derivative notation where they just say something like this, d to the n. So if you are reading something and there's a capital D raised to the n, that just means derivative of whatever the n is. It could be a third derivative, second derivative, any type of value for n. Usually n is a whole number. It's not fractions. But the idea is that there's an appeal of writing like this because it's just easy on the eyes. Okay, so believe it or not, this this equation that I'm writing basically is the same thing as a linear is the definition of what a linear DE is, but it's just written as capital D notation like this. Okay, so if you had plugged in, oh, I don't know, like n equals 3, n equals 3 is going to be basically a function you're going to differentiate, you'd basically result back into this. But try to get used to looking at it like this, okay, with capital D's in here, because it's just another way of writing it, and sometimes it might be written like this instead of the former way. And yeah, here, I'll give an example, okay? So what if we had something like this, okay? Let's say we had x squared, we had some second derivative. Okay, let's say we had some other function of x, then we had another derivative. Okay, but we might need a y in here to make this work out. So anyway, so let's say we have y. Let's say that we're taking a derivative of just y. Okay, so if we take a derivative of y, we're just going to get what? Y prime, right? If we take a second derivative of y, okay, we get y double prime, and then we just insert them into this equation, and then it works out. The single y, I'll have to think about that. But anyway, so there's this concept called a polynomial operator, and it's very similar to basically the format of a linear DE. And just so that you can write derivatives as primes, you can also write them as capital D's. That's the whole idea here. Okay, so if somebody did this, okay, if somebody had this, okay, what would this be equal to? We kind of talked about it, but what would this be equal to? It's just y double prime, right? Right? What if you had something like this? What is this equal to? Well, yeah, it's just a y to the nth, but it's not just y to the n, it's the y to the nth derivative. Yes, yes, nth derivative. So yeah, so just be familiar with the different ways of writing these derivatives. And sometimes they just put the d's in there just to make it look better on the eyes. Okay, so there's this theorem we're going to talk about, okay? There's a theorem. Okay, and this is called superposition. Okay, so if you have, okay, let's say that you have some function y, some other function y, you have a bunch of y's, okay? These are just functions, okay? But they're not just functions, they're also solutions, okay? You have these, they're solutions, right? and they're solutions to your differential equation, okay? And your differential equation, it might be in this type of format where you have something like this, kind of like what we've been talking about. And the n represents derivatives here. Also, I don't know if I talked about this or not, but right here, okay, where you have a sub n of x, that's just a coefficient in front of the y, right? But over here, the n minus 1, that just means it's the next coefficient, okay? There's nothing special about it. It just means that you have one coefficient and then you have another coefficient. And also this whole n and n minus 1, all that means is that if this is a second order differential equation, okay, then it's going to go 2, 1, and then 0, okay? So it just means everything's in descending order, okay? Anyway, so if you have these solutions, okay, you can literally take, okay, you can take these solutions and you can multiply them by constants, okay? And you can add them all up, and this new solution, okay, is also a solution, okay? So this is basically a special idea here that just so happens to work that you need to be familiar with. So let me try to explain this a little bit more. Okay, so this y1, this is a solution. This y2, this is a solution. And we're over here making a new solution, okay? And all we're doing is just basically taking all of our previous solutions, adding them up, but then multiplying them by some type of constant, okay? So this right here, also a solution, okay? So it's called superposition because you have two solutions, and if those are solutions, then you can add those together and make a new solution, and that's also another solution. So it's just a fun fact to know. All right. And what I would like for you guys to do is, I'm going to give you some examples here, and I'd like for you to try them. And they take a long time to do, so I'd like for you to maybe try them at home and just see how they work. Okay, so what if we have something like this, okay? We have y1 that's equal to x squared, okay? So then we have another y. We're going to call it y2. That's equal to this, x squared times ln, okay? So y1 and y2 are both solutions, okay? Both of these are solutions. So what can we say about the superposition principle? And let me write out what they're solutions to. So these are solutions to this guy. Okay, so this is a differential equation right here. And also note that in this differential equation, this is a third order differential equation. This has a y triple prime on it, okay? So this is third order, okay? And I don't think we know any techniques on how to solve this yet. Anyway, but the whole idea is that if x squared is a solution and x squared times ln is also a solution, then you can say there's a third solution, and it is a constant times the first solution plus a constant times the second solution, just like this, okay? So this is also a solution. So just take a moment real quick and think about this, okay? If you have some solutions, you can add them and get more solutions. Oh, that's interesting. Can that go on indefinitely? So think about that. Is there technically an infinite number of solutions? If you can always just take solutions and add them together with new constants and make more solutions. So my question to you guys, think about it, and then we'll talk about this next time. Is there, with the superposition principle, an infinite number of solutions? Okay, given that a set of solutions does exist. Okay, so that's a question. Think about it. We'll talk about it next time. Because according to this, and this is another thing I want you guys to check. Okay, according to this theorem, okay, I want you to check if you can take a constant multiple, okay, and add them to each other, okay, to make a new solution using previous solutions. Are these also solutions? I'm going to write some, okay? If I have this, y equals c1 times x squared plus c2 times x, okay? It's the same solution, but it has a different constant multiple in front of it. So I want you to go home and check, is this a solution to this based on superposition principle, okay? And we're not going to do it because, whatchamacallit, this is like a triple prime, okay? This is going to take a long time. But check, is this a solution here? And then you can even do other combinations. You could do something like this. Is this a solution? We have c1 times x squared ln x, and then you have some other c times x squared ln x. Can you double up on one solution but a different constant? So go home and see if these work out, okay? So the main concept to take away here is you have this idea called superposition principle, and if you have a set of solutions, then you can make another solution using using the addition of the previous solutions with constant multiples in front. So that's just a fact of differential equations, okay? So any questions over anything so far? Right now, we're just taking in a lot of fun facts and information. Okay, so I'm going to clear this, okay? And I'm going to post all these notes like I've been doing. Okay, has anybody heard of this? Linear dependence and independence. Okay, has anybody heard of linear dependent and linear independent? Has anybody heard of these concepts? We've talked about linear equations, right? There's y equals mx plus b, that's linear. There's linear differential equations, but this is linear dependence and independence. It's a little bit, it's actually totally, it's a different concept. So any guess on this? Okay, you might have seen something like this. Maybe you might have seen it in the college algebra days. Okay, what if I had something like this? Okay, this is a matrix. Okay, this is a matrix right here. Okay, and what's interesting about this is that, did you know, this is very interesting, okay? These rows right here, right? You have rows and you have columns, right? But anyway, these rows, you can treat them as if it's a vector, okay? And so basically, you can have a vector like this, okay? So, and then, okay, so you could have V1, and then you can have, you could have V2, okay? I put this little arrow at the top, okay? If you see something that has an arrow at the top, usually that indicates it's a vector, okay? And this is just a vector of three variables, right? X, Y, and Z, okay? So we have these three vectors, right? There's a way to check if these are, if this set is independent or dependent, okay? And I'll tell you how you're supposed to do it. Okay, everybody knows how to row reduce, right? Everybody knows how to row reduce this, okay? You're supposed to get something like this: 1, 1, 1, 0, 0, 0, 0, 0, 0, and then you get some type of value here, and value here. Everybody's familiar with this, right? And again, this is your X, Y, and your Z. And what you want is you want that diagonal of ones, okay? You want that diagonal of ones because there's something magical happens when you get that. You end up getting 1x equals A, you get 1y equals B, and you get 1z equals C, okay? Okay, so here's the thing. If you take three vectors, you plug them into a matrix, okay? And of course, these could be different sizes and stuff. I just picked a 3 by 3 just for fun. But if you take these vectors, put them into a matrix, and you row reduce to get get the diagonal of ones, if you get a solution, if you get one solution and one solution only, it's called independent. Okay, so it's called linear independent if you get one solution. Okay. So you've probably heard of this, but they may have not have used this terminology. But when you're solving for something and you get one solution, it's called an independent solution, okay? So, okay, so based off of that, tell me, how would we get a linear dependent solution? How would we do that? Can anybody guess? It's the same idea, okay? I'm going to clear this real quick. Okay, I'm going to clear this. So what if we had something like this? What if we had something... Okay, these are different vectors now, okay? Different vectors, okay? We put them in a matrix, okay? We're trying to solve this. I want somebody to tell me what's different about this one that that we didn't see in the other one. Okay, so just think for a second. Okay, I'll give you just a minute or two. Tell me what's different about this one that wasn't like the other one, and I'll write the other one out too. Okay, okay, somebody has it. Okay. Okay, so this is what I want you to look at. If you look at this one right here, okay, and if you look at this one right here, okay, they're just the same, okay? And it turns out that if you have two vectors that are the same, or, okay, or if you have one vector, v1, or that is related to another vector by some type of constant multiple, right? Like let's say that row 2 was multiplied by 2, okay? Let's say it was this. Let's say we had 1, 2, 2, 0, but then the second row was 2, 4, 4, 0, okay? It'd be the same concept, okay? So if you have two vectors that are the same, or they are the same but off by a constant multiple, this is going to be called linear dependent, okay? All right? And so here's the thing. Can anybody tell me, if I were to solve, if I were to do, it's called RREF, row reduced echelon form. If I were to take this matrix and row reduce it, what would I get? I'm going to get something that wasn't like what we got over here. Remember over here we had 1, 1, 1, right? Okay, we had the 1, 1, 1. What would I get over here? I'm going to get something that's a little bit different. I might get this. I might get 1, 1. But if you do row operations on this, you might actually cancel out the entire bottom row. Okay? Okay, so if you cancel out the entire bottom row, you get infinite solutions, okay? Because you do something called back substitution, and then you basically solve for X, Y, and Z still, but you have the solution in terms, one solution is in terms of another variable, hence infinite solutions, okay? Okay, so that's linear independence and dependence, but the thing is that we're going to talk about this in terms of not just matrices, but we're going to talk about it in terms of differential equations, okay? So, we're going to talk, okay? So let me print screen this, and then I'm going to give you some examples, and we're going to talk about them. Okay, so what if I gave you this, okay? What if I gave you f1, and that equals x squared, and then I gave you f2, and that equals 2x squared. And I said, are these linear independent or dependent? Which one is it? And I'm going to say linear independent abbreviated or linear LD, LI for linear independent and LD for linear dependent abbreviation. So these two functions, we're not looking at a matrix anymore. We're not looking at vectors. We're looking at two different functions. Is this linear independent or linear dependent? You guys take a guess. Okay, yes, okay. Okay, and so somebody said linear dependent for these two different functions, okay? So can somebody elaborate on that and tell me why is it, how did you know? Like, how did you know? Oh, okay, somebody wrote two are the same, right? I can't remember if that's your last, if that's what you said last time or if it's new. Anyway, they're, oh, okay, this is what I'm trying to say. They differ by a constant, okay? So they're the same, they only differ by a constant. If one function is a constant multiple of another function, it's going to be linear independent. Linear dependent, okay? So one function is a constant multiple of the other function. Okay? All right, great. So what if I gave you this? Okay? What if I gave you two different functions? What if I said, okay, f1 is going to be it's going to be x, f2 is going to be absolute value of x. Okay, what about these two functions? Okay, you guys tell me, is this linear independent or linear dependent? So linear independent or linear dependent? Okay, okay. So in the previous one, they were off by a constant multiple. Now, okay, so here's the tricky thing. X and absolute value of X, like they both have a constant multiple of 1, right? Anyway, the whole idea, they look very similar, right? In fact, um, whatchamacallit, the only real difference is that um, in quadrants, what? In quadrants 2 and 3, the absolute value, if you flip the y values in quadrants 2 and 3, you actually get the function just f of x equals x, okay? They're very similar to each other, but here's the thing. They're not off by a constant multiple, right? They are two totally different functions, right? Okay? Uh, the function y equals x, that's this diagonal line, and then the absolute value is this v shape, right? Okay, so these functions are not the same function, but just multiplied by a different constant. So they're going to be called linear independent, okay? So this is, okay. So if you were to look at these two functions and you were to see, if you were to decide if they're independent or dependent, they're going to be dependent, okay? All right, so now we're going to actually talk about like the definition. There's a couple weird, there's like a really weird definition that describes this, okay? Um, it may not make sense when you see it, but there's a couple different ways of looking at this, but I'm going to basically present a definition now. Okay, so the definition is this. Okay, we have this equation. Okay, we have this equation. It's C1, okay, times some type of function, C2 times some type of function, okay? And everybody knows what the plus dot 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 means, right? Everybody knows that. It just means it's a continuation of the pattern. Okay, so if you have something like this, okay, these functions, okay, these functions, or I should say set of functions, let me try to type it out. Okay, so all of these f's right here, this, okay, if, okay, so this is linear independent if all of the c's, let me try to write this in the most understandable way. If all of the c's, okay, basically if you can plug in a 0, we're going to say if all of the c's are 0, okay, if you can find a 0 for every c, okay, and plug it in here, and the left-hand side ends up being all 0, and the right-hand side is 0 by definition. If all of the c's are 0, okay, then it satisfies this criteria for being linear independent, okay? This is kind of confusing because in the book, they state their definition in terms of linear dependence, and they basically reverse this entire definition, okay? So basically, follow this definition. If this definition to me makes the most sense. So you have this equation, you have all of these functions, you have all of these c's. If you can find, if the only thing that makes the left-hand side 0 is all of your c's, okay? If all of your c's are 0, then this will be linear independent. So let's try to have some examples here. Okay. So so for example, okay. So this is just an example. If you had some functions and you got a c value for your functions that was not 0, it's not linear independent. Okay. So watch this. Okay, let's say we have two functions. Okay, we have C1, we have F1, okay, and then we have C2, F2, okay? So we only have two functions in this case. We don't have more than that. And the functions that we have, okay, we have 1 times x squared, okay? And then we have 2 times x squared, okay? So the functions themselves produce the constants in this case, okay? So the thing is that these two functions, okay, according to this definition, how could you give me an argument for whether this is linear independent or linear dependent, okay? So, and we kind of, I think we already did these two functions, so we know the answer, but I want you to give me some type of explanation for what the outcome is, okay? So what's the outcome and what's the explanation? Somebody tell me. So, okay, so is it linear independent or linear dependent? And I think we already know the answer to this. Because the two functions were just x squared and 2 times x squared. So what is that? Independent or dependent? Well, well, if you have one function that's a constant multiple of the other, it's linear dependent, right? Okay? Independent means that the functions have no relationship. They're completely different functions, okay? So it's linear dependent, okay, because one is a constant multiple of the other. But remember, I just wrote out this weird formula right here, right? And I said you need to be able to find, you need to be able to, all of the C's basically need to be 0 in order to satisfy this. And all of your C's that are, if you can basically set C's equal to 0, and that satisfies this equation, then it's linear independent, right? So linear independent. Okay, so watch this, okay? Here, this is C1, okay? Here, this is C2, okay? Both C1 does not equal 0, and C2 does not equal 0, okay? So we're wanting C to be 0, okay? So anyway, your C's are not zeros, but if you were to add these, okay, if you were to add these and you were to get 3 times x squared, okay, equals 0, there's no way, because this is like your constant, okay? I thought you meant plug in 0 for the C's. Well, okay, you kind of, okay, for linear independent, yes, okay? Okay, this is a really weird concept. Just go with me, okay? Okay, do you see this equation right here? Okay, do you see this equation right here? We have 3x squared equals 0, and that was based off of these two functions, 1x squared and 2x squared. Okay, that makes 3x squared equals 0. Okay, your C is like the constant in front. Okay, so the thing is that to satisfy this solution, there is no such C which makes this true, okay? The C has already been chosen. It already exists, and the constant is 3, okay? So you can't pick you can't pick a value for C that you can't find a value for C that satisfies this. Yes, it's true that x equals 0 satisfies this, but according to this definition, we want to be able to find all C's that basically make this 0, okay? And the C is equal to 3, and so we can't find a C that's 0 to satisfy this solution. So linear dependent. So it's not only linear dependent because one function is a multiple of another, but it's also linear dependent because we can't find a c that will make this equation true, where both sides, the left-hand side and the right-hand side, are 0. Okay? Okay. So this is linear dependent, okay? So we are going to do linear independent, okay? Okay. So remember, just a minute ago, we just said, okay, we just said a minute ago that the functions x and absolute value of x, okay, we just said that these functions were linear independent, okay? So let's see if that works, okay, in terms of that definition where we have the c's times the functions, the c values times the function values. Anyway, so if I have c1, this is the format, okay? C1 times F1, we have C2 times F2, okay, equal to 0. Okay, we have C1 times F1, which is just x. We have C2 times absolute value for x, okay? So, can we find two C's such that, this equation is satisfied? Because if I pick C1 is equal to 0, and I pick C2 is equal to 0, okay, then I have this, okay? Well, this is 0 plus 0 equals 0. This is true, okay? And we call this linear independent. Okay, so on the last example, we could not, because the functions were the same, we were able to basically group coefficients, and that took the place of a c value, okay? So in this situation, we can't combine these functions, okay? And we can find c values that make this true. But in the last one, we couldn't, okay? Um, so any questions on this? And as a fun example, I want you guys to pick two functions, and we're going to see if they're linear independent or not, okay? So think for a second. Pick two different functions that are linear independent and two functions that are not linear independent, and we're going to look. So somebody in the comments basically pick two functions, and we're going to see if they're linear independent or not. And while you're thinking about that, there was actually an example that I came across that I really liked. And the example was this. Okay, all right, so somebody wrote some functions down. Okay, we're going to get into that in just a second. Look at these two functions right here, okay? We have one function that is 2 times sine x cosine x. We have another function that is sine 2x. So if I put this on the exam and said, is this linear independent or dependent, what would you guys say? Is it linear, these two functions, is it linear independent or linear dependent? Okay, so linear dependent. Okay, so how come? These functions don't look the same, right? So they're linear dependent because they rely on x? Is that? So um, the answer is correct that it's linear dependent. Okay, this is correct, but why? So think about it. Oh, okay. These are not related with a derivative. Okay. Okay. Watch this. Okay. If we took a derivative of this, okay, derivative of sine 2x is what? It's cosine 2x times 2, okay? So yes, it is true that the derivative is a constant multiple of another function. There's a constant multiple in there, but the derivative has nothing to do, well, we will later find out that the derivative actually does have something to do with linear dependent and linear independent. So the derivative does, okay, somebody said it. It's the same identity, okay? Okay. So 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 the thing is that we will find out actually later in today's lecture, okay, that the derivative can play a role in finding out if two functions are linear independent or linear dependent, okay? But as someone stated, it's the same identity, right? Okay? This is the same formula. It's called actually it's called a double, right? Double angle formula. So sine 2x is just the double angle formula, and that turns into 2 times sine times cosine. So because they're the same function, linear dependent, okay? So we'll do one more, okay? So somebody said e to the, oh, look at this. Somebody said this. Somebody mentioned we have e to the 2x, and then we have 2e to the 2x, okay? Now, what's really interesting is that, remember, this function, e to the x, this is the only function that returns its exact self, right? Of course, if you have an exponent in here, you can get a constant multiple of this. So, that's an excellent example of something that's linear dependent, okay? It's linear dependent because you have one function and then you have a constant multiple of that same function. Anytime you run into that situation, you're going to call it linear dependent. If you did these two functions, e to the 2x, and then you had 2x, okay? If you had e to the 2x and then 2x, this is linear independent because these functions are not related to each other in any way. They are not constant multiples of each other, okay? Okay, so you get the idea, right? You get the idea. If it's a constant multiple, linear dependent, not a constant multiple, linear independent, okay? Anyway, so what I'm going to show you now is there's a systematic way to show, okay? There's actually a procedure to show this, okay? So let me write here. So there's this, everybody knows what a determinant is, right? Okay, right? We might do a quick example here, okay? For example, okay, somebody said part of the quadratic equation. Quadratic equation looks like this. Um, oh, um, oh, um, actually, I think, okay. Okay, determinant is part of a matrix. This right here is called the discriminant, okay? There's another name for this, okay? But this basically depends on if you're going to have one solution, two solutions, or two complex solutions, okay? This is called the discriminant, okay? The determinant is something much different, okay? The determinant is used when you're talking about matrices, okay? So watch this. Here's a matrix, right? And you can do this in your calculator if you have a graphing calculator, okay? I'm just going to throw in some numbers here, okay? I'm just making this up, but, okay? So this is a 2 by 2, okay? So how would you figure out what the determinant is of this? So you're going to use this formula, okay? And this formula basically is, of course, this is a 2 by 2. It gets different as you get bigger and bigger matrices. Okay? The formula for a 2 by 2 is you take this number and you multiply it by this number. Okay? So you have 1, okay, times 2. Okay? Then what you do is you take this number and you multiply it by this number. But you subtract these. Okay? So you know, where does this come from? Who came up with this? This is a property of matrices, and it's very useful when you're doing all kinds of interesting problems using matrices. Um, so anyway, so the determinant of this, okay, and this is equal to det, the determinant. This is equal to what? Oh yeah, and what is it? This has to deal with something, whether it's invertible or not, right? Okay, so this is just minus 13, okay? So the thing is that determinants are a way to check to see if matrices are invertible or not. Invertible means if it has an inverse, okay? And so if your determinant is equal to 0, there's no inverse. Okay, so this is a very important property, okay? But anyway, there is a special, basically, determinant that we can create called the Wronskian, and that can decide if something is linear independent or dependent. So it basically, there's a systematic approach that takes all of the guesswork out of this, okay? So, and we're going to do that, okay? So let me do a clean page here, okay? Let me do a clean page. Okay, so this is what we're going to do. Consider this, okay? Consider y double prime minus 9y equals 0, okay? And this has a solution set, okay? Has a solution set of y1 equals this, okay? And also y2 is equal to this, okay? So if you had to guess, okay, if you had to guess, are these two functions, y1 and y2, they're also solutions, are these linear, independent, or dependent? Take a guess now, and then we're going to actually like prove it using this Wronskian determinant. We're going to prove it, Okay, so place your bets now. Is this linear independent or dependent? You guys tell me. These two functions, e to the 3x and e to the negative 3x. Independent or dependent? Well, okay. Somebody said dependent. Are you sure? Because remember, it has to be a constant multiple. One function is a constant multiple of another function for it to be dependent. It's just kind of like those vectors in the matrix. If one vector is the same vector or a constant multiple of another vector, it's dependent. So, okay, so it's going to be linear independent, okay? Okay, it's gonna be linear independent, but we're going to prove it now, okay? So we're going to use this determinant, okay, called the Wronskian. And what the Wronskian is it's going to look like this, okay? You place your functions in here, okay? F1, F2, however many you have, okay? You place your functions in here. But what's interesting is that on the second row, you get derivatives, okay? So oddly enough, if you take functions and you take their derivatives and you put it in a matrix and you take the determinant of it, you can actually determine whether it's linear, independent, or dependent. Okay? So very interesting that that's even a thing, okay? So if you have this, okay, you take a determinant of this, okay? Take a determinant of W, okay? And what you're looking for is you're looking for this to not equal 0, okay? And that means linear independent. And here's the whole, okay, here's something very, very cool and very awesome, okay? We just basically said something, okay? We said something just a second ago. Remember how I said if you have matrix A, okay? If you have matrix A and you take the determinant of that, okay, and you get 0, it's not invertible, right? Okay? So the thing is that if it's not, if something is invertible, and in other words, if it has an inverse, then it implies linear independence, okay? And if there's no inverse, then that implies linear dependence, okay? So very, very interesting here, okay? So basically, when you're looking at matrices and you're looking at the determinants, knowing whether the determinant is 0 or not is a big deal. Because if you can take the determinant of something and it's non-zero, then you know it has an inverse and it's linear independent. If you get 0 for your inverse, it's bad, because the reasons why it's bad is because if you have like a 2 by 2 matrix, okay, if you have a 2 by 2 matrix, okay, and okay, the formula for the inverse is 1 over the determinant, okay, times some other stuff, okay? So if your determinant is 0, okay, if your determinant equals 0, then you're dividing by 0, which is like, you can't do that, okay? So in other words, we have this Wronskian, okay, and we're going to do that using these functions. And what you're looking for is you take the determinant of the Wronskian, and if it does not equal 0, it's linear independent, okay? And we're going to do that using those two functions I wrote on the very next slide here. Okay, so we're going to clear this, and I'm going to write the same problem again because I kind of ran out of room. But anyway, here we go. Okay, so you have y1 equals e to the 3x, okay? You have y2 equals e to the negative 3x, okay? We know that these are linear independent because they're not a constant multiple of another one, okay, of each other. But let's use the Wronskian technique and take the determinant to find out for sure, okay? So plug in one function, plug in your y1 here, right? But directly below it, take a derivative of this, okay? Then take your y2, okay? Here we go. Then take a derivative of this, okay? All right, great. Now do the determinant, okay? And remember, it's this one times this one minus this one times this one. So let's do that. Here we go. We have e to the negative 3x times 3e to the 3x. And then we have a subtraction. We have e to the 3x times negative e to the negative 3x. Okay, so let's see what's going to happen here. Well, e to the negative 3x and e to the 3x, these are the same function, just one over each other. So that becomes 3, okay? Because these two functions just become 1, okay? Now we have two negatives. Well, that becomes a positive. Okay, great, right? So this is a positive, this is a positive. And what's going to happen here? Well, this happens, okay? You just get the constant in front, okay? Because really this is division. The negative means it's on the bottom, it divides out. And so we end up getting 6, and we all know 6 is not equal to 0. So this is the whole this is the whole magic of this whole idea, is that is that we have now proven that this is linear independent, because the determinant of this Wronskian with these two functions was not equal to 0. Linear independent. Okay, and that's basically all for today. And we're going to pick up, there's still like a couple more things on this section that we're going to talk about. But basically we're going to wrap up basically the rest of this section and then start on the next section next time. Another thing that I'm going to do is I will be getting the exams back to you probably by Wednesday, and so you can see what you missed or whatever. Does anybody have any questions over anything so far? So yeah, so this is section 4.1, okay? And try to do some of those homework problems for this section, okay? Try to do some of those. And if you get stuck,
And I have a question about the test, one of the test questions.
yeah.
Yeah, I was wondering if you could, I guess next time, go over number, I think it was number, let me see here. I think it was number 7 on the exam, which was, I had it earlier, I can't find it.
Okay, I'm pulling up the exam right now. Oh, okay, so number 7. Oh, okay, so what was your question on number 7? That was just solving a linear differential equation, okay?
Yeah, and I couldn't figure that one out. That's why I was wondering if you were going to go over some of these next time.
Okay, well, I'll tell you this. Okay, so solving that's basically solving a standard linear differential equation, number 7. So here's the deal, okay? If you have a question on that, look in the book or look online. Just look up some basic examples of solving a linear differential equation where you have an integration factor.
Oh,
Look that
no,
up.
I knew how to basically solve it. It's that 2 minus sine x, e to 2 minus sine x is what totally hosed me on all that. And so I didn't know if you were
Oh,
supposed
okay.
to do a u substitution on that or not, but that's why I was.
Okay. Well, okay. So I'm going to give you a hint, okay? I'll give you a hint right now, okay? So the thing is that it's e to the what? 2 over 2 minus sine x, okay? Okay, so basically, this is testing you over properties where you're dealing with powers. For example, if you have x to the n times x to the m, This is the addition of powers, right? So the thing is that this is going to be what? You're going to separate this into 2 over 2 minus this, okay? So you have e to the 1, and then you also have times e to the negative sine x over 2. So that's what this turns into. So what's really interesting is this right here, e to the 2 minus sine x divided by 2, that's the same thing as e to the 1 being multiplied by e to the negative sine x divided by 2. You're just, all you're doing is you're adding fractions together, but they're really exponents, and it's because the base is the same. E is considered the base here, and it's the same on both of these functions. So when you multiply two functions with the same base, you add the exponents. So once you know, so okay, so try the problem again, knowing that information now.
I tried that problem for several days.
All right, well, okay, well, try it again. Just know that you can write it as e to the 1 times e to the negative sine x over 2.
Yeah, I'll look at it.
Okay, all right. Well, try to work on some of the problems in the homework, and basically that's it for today. And I'll see you Wednesday, and I'll try to have the I'll basically wrap up finishing grading the exams. Oh yeah. You'll get the exam back on what you did wrong. I just haven't given them back because I hadn't gotten them all at the time that I had graded them. So exams not given back yet. Okay, so if you have any questions over anything, let me know now. Otherwise, I will see you on
So
Wednesday.
I have a question on that number 7. So basically, that problem, the e minus e to the minus sine x over 2 is going to cancel out, and you're left with e to the 1 power for all of it. And then you start doing your integration after that.
Yeah, okay, so here's another hint, okay? When you're doing that problem, number 7 on the exam, you're going to get your integration factor, right? I can't remember what it is off the top of my head, but you're going to multiply it through
It's e to the sine x over 2. And so
yeah. So e to the sine x over 2. So yeah, it looks like e will just be left over. E to the 1 will be left over, but the e to the negative sine x over 2 will be canceled, right?
right.
Okay, so basically the integration factor will cancel the whole e to the sine x out and just leave e, simplifying the dE.
Okay. But you're still left with y to the e to the sine x over 2. And then, yeah,
Well, try to work it one more time and just be very careful with your math. And again, now that you know that this will cancel out, you should just get e on the right hand side, and then the
no,
left hand side will be.
but you're gonna, for the left hand side, you're gonna be left with y prime plus y to the e sine x over 2,
Okay,
and it's equal
and
to,
just one more hint. On the left-hand side, okay, on the left-hand side, it's going to be a reverse product rule. It's going to be a derivative of your function of y and your integration factor, right? Okay, so so basically you're looking at this, okay? So and then you integrate both sides, okay? So whatever you got for your integration factor, that's going to be multiplied by your y, and you're going to write that as a product of two functions, but you're going to write it as a derivative of a product of two functions on the left-hand side, okay? So if you can get your integration factor, and you know that on the right-hand side that integration factor is going to cancel with e to the negative sine x over 2, then you're going to end up with something like this that I'm circling right here. And that should at least get you, you're like halfway done at that point. Then just integrate both sides and go from there. So try it again and see if you get it. And if you still haven't gotten it by Wednesday, maybe we could talk about it.
Okay.
All right. Well, anyway, so that's it for today. So I'll see you Wednesday. So just keep on working at it.